So in the final set of slides, we're going to look at the common cause analysis. So we're going to look at a particular risk analysis, common mode analysis, and the zonal safety analysis. I got this little example in here regarding the wire bundles, and I'll get back to that here in a second. Now basically what we're doing in a common cause analysis, what a common cause analysis does, is that it establishes and validates the physical and functional separation and isolation requirements between systems, and also verifies that these requirements have been met. So you do a couple things. You look at where systems are located in an aircraft, and you're going to truly identify if these systems are independent, given the internal aircraft environment, in other words, where these boxes are located within the aircraft, or given outside disturbances and environments. First of all, in the zonal safety assessment. The zonal safety assessment, you're going to break down the aircraft in a set of zones, and you're going to identify, how these avionics boxes are installed within that zone, and if the installation meets the safety requirements. So you're going to make sure that there's no interference between the system that would result in a violation of the independence requirement that you assumed maybe in your fault tree analysis. You're also going to check out if there's any potential for errors due to maintenance. That if you try to maintain one box which is next to another box, is that due to maintenance error, these other boxes may be affected as well. These are problems. And this wire bundle is one of these examples. You see that these bundles run through a particular zone of the aircraft. And in this case, each one of these bundles may be associated with a different system, but since they're all so close together, it could mean that if there is a local, for example, a leak above it that causes corrosion of these cases, like was one of the possible scenarios that you saw with TWA-800, the accident, is that would increase the likelihood of a crack in this spot, resulting in arcing between systems, whereas the systems are no longer independent. So that's basically what you do in a zonal safety analysis. And here you see more or less the basic zones that you could break it down into. And of course, this is just an example that I got from ARP4761. A particular risk analysis really starts looking at external influences or disturbances. These external influences or disturbances could potentially cause multiple systems to fail, resulting in a violation of the independency claim. If fire breaks out, this could affect multiple systems that you previously thought were independent. You can also have hail, snow, you can have a bird strike that would take out an engine, but maybe also some other hydraulic cables. Lightning, could cause you to lose a significant amount of the electronic system board of an aircraft, etc., etc. These are what we call particular risks, and they could lead to multiple failures at the same time of systems that you previously thought were independent. So in a particular risk analysis, you're going to analyze what these risks really are. In a common mode analysis, you're going to verify, you're going to go to the fault tree analysis, the data dependency diagrams, the Markov analysis, identify and verify if the independency is met. In terms of hardware design, or for example, hardware errors. There could be hardware errors, for example, in the design of coding that are common because of common design teams or common approaches used in the hardware and software design. There could also be common errors in the production chain that cause different boxes to have the same failure mode that you had not taken into account in your fault tree, for example. Could be problems with your requirements, etc., etc. So in other words, you're trying to verify if independence is truly there. Now, in a lot of cases, when we have a potential problem or like a latent failure, for example, we tend to add a monitor function to it. And what the monitor function really does, it checks out if a failure does occur, and if it occurs, it provides the user, for example, the flight crew or the pilot, with a warning. So in that case, the pilot can still perform any mitigating actions, and that's why I put this slide here. Well, the next two slides kind of talk a little bit about software and hardware reliability and the difference between both of them. You know, basically the stuff we've talked about so far is really being hardware oriented. And of course, failures there are typically due to some deficiencies in design, production, or maintenance, or they just the reliability just decrease as a function of time. With software, this is different. You know, the failure rate, the probability may not increase. That something fails may not increase over time. Okay. So the slides are pretty self-explanatory. So definitely make sure to go through these. Now, finally, one thing I want to talk about is the way you can deal with software failures. Now, you can actually do software avoidance, in which you try to prevent that software faults presence, and these typically are associated with you coming up with a very well-structured approach to designing your software. So you do structured programming, you make use of reuse of components that you have used extensively and have proven themselves in the field. Things like formal method, model-based design. You try to do a very structured manner when you design your software. So this way you try to prevent software faults. Now, of course, the second way to deal with software is fault removal, or you should try to detect the faults, identify where they are, and then get rid of them. And of course, this is what you typically do in a verification and validation process. You do this by software testing. And then finally, of course, fault tolerance. And fault tolerance, of course, is typically also a little bit more system-wide, where you say that you build your system such that even if there's errors, it still can continue operation. And this has to do, for example, with triple redundancy. Think if you have a triple redundant system, you have 3 identical components. In some case, in terms of hardware, that means that all 3 needs to fail. In other words, it's a parallel system. With software, you can do similar things. So in software fault tolerance, you say, okay, these are the methods that you can use to actually make sure that the software can tolerate multiple faults.